Okay, this is the second hour of Physics 1C for June 3rd, and we're now going to be talking about the energy and momentum of EM waves. Okay, so we derived a while back these ideas of electromagnetic energy density. With the electric field, we said that the energy density was given by this expression, an expression that we derived way back in, I think it was chapter 26 or something, the chapter on capacitors. We derived this expression. For the magnetic field, we derived this expression, which was 1/2 mu naught in the denominator, and then b squared right here. And what both of these represent is the energy per unit volume. So this is these both represent energy density, or energy per unit volume. And we said that if you have something that has both electric and magnetic fields in it, then you just get the sum of this. So the total energy density would be 1/2 epsilon naught E squared plus 1/2 mu naught B squared. And we've also learned just now that if you take the ratio of the electric field to the magnetic field, that this is equal to the speed of light. And I said before that it was just the maximum values of these, but it's also true that for a wave that's in phase, that the ratio of these will always be equal to the speed of light. And basically for waves in free space. So we can basically use that to simplify our equation right here. If we do that, we can write this like this. So instead of b squared here, we're just going to say that b is equal to e over c. So we're going to have e squared over c squared. The next thing we can do is to use the relationship that c is equal to 1 over the square root of mu naught epsilon naught, or that c squared is 1 over mu naught epsilon naught. So we have c squared showing up here in the denominator, so if we replace that, so the c squared is down here, right? So we're going to put this in the numerator. Then these mu's will cancel, and what we're going to end up getting is we have 1/2 epsilon naught e squared, 1/2 epsilon naught e squared. So you add the 1/2, so you get a 1, and we end up just getting epsilon naught times e squared. So this would represent the energy density of an electromagnetic wave. Okay. Does that make sense to everyone? We just went through there?
Yeah, it makes sense.
All right. So the next thing we want to do is to look at the way in which these waves transport energy. We'd like to know kind of the rate at which energy is transferred. So we're going to use this picture from the book, so I don't have to try to redraw it since it's three-dimensional. Their version is going to look better than mine for sure. And we're going to use this to define the energy per unit time that is transferred by these waves, because these electromagnetic waves definitely transport energy. As an example, the sun is sending electromagnetic waves toward the Earth constantly, and there's a rate at which that energy is flowing to Earth, and we can calculate that, and we can also use it if we want to find, for example, what the electric field of those waves is. All right, so here's our picture. So it's our same wavefront kind of concept. We have two different wavefronts here. And the idea is that our wavefront has moved in space between the point on the left and the point on the right, right? So it says the stationary plane and then a wavefront at a time dt later. The coordinate system here is so that x is this way, z is coming out, and y is up. And we're looking at a wavefront that is moved from this position to this position in some time that is called dt, which means that the distance between the wavefronts would be c times dt because it's moving at a speed c. So if the wavefront is moving along at a speed c, then the distance it travels is c times the time interval. And what we're going to do now is we're going to kind of calculate this thing that we call the Poynting vector. Okay, so I haven't really taught 1D before, but they always tell me it is a very important thing that shows up in 1D, the Poynting vector. So I'm assuming you're going to use it a little bit when you're talking about optics in that class. Hey, why didn't it change? It's got my... Right, there we go. Okay, so keeping what we just calculated, what we're going to do is we're going to say that we want to calculate the amount of energy there is in this region right here. And the way that we can do that is to say that there's some amount of energy du that's contained in this region, this little volume here, which is like a rectangular prism. And that should be equal to the energy density in that region multiplied by the volume in that region, so what we would probably call dV. So this little u is going to be this, the energy density. The big U on the left-hand side is going to be the total energy. Okay, if this equation is confusing, this is what this is saying is the energy in the box is equal to the energy per unit volume times the volume, right? That's all we're saying basically. So du, so this is capital. Maybe I make the capital U look like this or something, so it's kind of different than the lowercase u, which we could draw like this. dV in this case is going to be the volume of our box, where we're saying that the length of the box is cdt, and the area of the face of this is just called A. So we multiply by A right here. So u dV will be U times cdt times A. Just like it says up here. If we plug in the energy density right here, this is epsilon naught E squared C. I think we're going to move the dt to the other side, so we'll have du dt. Let me make this original u the same kind of u. Okay, du dt equals epsilon naught E squared for a little u, c dt, we move the dt over here, multiplied by A. I think we're going to move the A to the other side too. Yeah, let's do that. So 1 over A. And then we're going to manipulate this equation on the right-hand side. So epsilon naught E squared C. What's that equal to? Well, we know that C is equal to 1 over the square root of mu naught times epsilon naught. And I think we want mu naught to show up in the denominator here. So we're going to eliminate epsilon naught now in favor of C and mu naught. Is that what we're doing? Oh, that's because we need another equation. I was like, this isn't going to work. We also need this. The speed of light is going to be equal to the ratio of the electric field divided by the magnetic field. So we want to get the magnetic field back into this equation. And we also want to get rid of epsilon naught for our final result. So the way that we're going to do that is to write... To get B in here, I think we need to write E squared should be equal to, according to this equation, since E is also equal to B times C, then E squared should be equal to, obviously, E times E. which would be E times B times C, right? So if we plug that into here, we're going to get epsilon naught E B C squared. And then we can replace the C squared with this. So we're going to have epsilon naught. We replace the C squared. So C squared is equal to 1 over mu naught epsilon naught. And then, yeah, the epsilon naughts will cancel. And we end up just getting E times B divided by mu naught. And all of this is equal to this on the left-hand side, which is 1 over A multiplied by du dt. Okay? So, what is du dt? Well, U is energy, right? It's the amount of energy that's contained in this box, right? So what would the derivative of that energy with respect to time be?
A power.
Power, right?
Yeah, power. So this to me looks like, let's scroll down just a little bit here. I think I write it on the right-hand side.
Like power per unit area?
It's it's basically power. That's what du dt is. That's the power. Divided by area. Okay? And we call this quantity the Poynting vector, and we use the symbol S. Okay, so S is, it's called the Poynting vector. Well, it's going to be a vector here in a second. Right now it's not a vector, obviously. It's just a quantity. We call it the Poynting vector. It has units of power per unit area. What is power per unit area normally referred to as in physics?
What is that?
What?
I'm thinking about like radiation and like,
Okay.
but there's a word for it. Power per unit area.
Yeah.
I'm thinking about like radiation being deposited and like something being irradiated.
Anyone remember?
The units be joules per second meters squared, right?
Yeah, or, well, how do you measure power? Power is measured as watts per meter squared. I don't know if that helps.
Yeah.
Yeah, watts per unit area. What?
Yeah, but there's a name for this.
Yeah, there's a name. There's a name for it. Yeah.
Does anyone remember?
It's called, is it intensity?
Intensity. Yeah, that's right.
Oh, well.
So if you're being showered with radiation, then if you take the amount of power at which it's depositing in a region, and you divide by the area, that tells you the intensity, right? Because if you take, let's say, 1,000 watts, okay, let's say you've got like 1,000-watt laser beam, right? You could either have that 1,000 watts spread over a large area, in which case it wouldn't be too intense, right? But if you take that 1,000 watts and you condense it down to a really tiny area, then it's going to be really intense, right? Yeah, intensity, right? So the Poynting vector, which I wonder if your Physics 1D teachers will get you to like this name. I really don't like the name because it's just the intensity of the energy, right? It's just the intensity of the radiation that you're talking about. Now let's describe it as a vector. So the way we define it as a vector is like this: S is equal to E cross B. So here's that E cross B thing that we've been doing all this time, divided by mu naught. So that's the official definition of what the Poynting vector is. For me, it just represents the intensity of the light that you're getting, right? When I say that word, I hope it means something to you. If you were to walk outside on a really bright day, and like, let's say you've been sitting inside and it's dark inside your house, you've been watching a movie or something like that, or you're at a theater and it's dark, and you walk outside and it's bright outside, that light's going to seem pretty intense to your eyes, right?
Yeah.
Whereas, right now it's pretty bright inside my house, so if I walk outdoors, the light's not going to be too intense to my eyes, and that's because mostly just your eyes get used to your surroundings and stuff like that, right? But that's what I think about when I think about the word intense, intensity, right? And the Poynting vector describes that. Okay, so the kind of common thing about the that we use to describe what this thing represents is solar panels. The light from the sun is coming down towards the Earth, and we pretty much know I guess this is something that is relevant. When you go outdoors, you're kind of surrounded by light, right? But you know that light is actually coming from the sun, right? Nonetheless, when you look all around you, everything's lit up, right? The houses and the dogs and the cats and the bushes and the trees, everything's lit up. So it might seem like light is just kind of everywhere, but the reality is that light is coming from somewhere, right? It's coming from the sun, and as the sun sends that light, it sends energy in this direction, basically, related to the direction of the propagation of the light that's coming from this E cross B thing, right? So if you want to maximize the amount of energy that you get from the sun, then what you need to do is you need to make sure that if you're using a solar panel, that it's facing the sun, right? This is a really, maybe even obvious idea. I don't know if it's super obvious, but so if I have a solar panel right here, and I have the sun, and it's sitting somewhere over here. Oh, come on, really? Let me pick this one. If I have the sun, and it's shining over here, right? The sun is obviously incredibly far away, so the rays of light, when they hit the Earth, they're all going to be moving in straight lines, basically, which means you're going to have these plane waves, right, that are flowing towards the Earth. And if the sun is kind of low in the sky, then your solar panel is only going to pick up so much of that energy, right? If you put your solar panel, let's say, on the top of a flat house, then the time when the sun gives you the maximum amount of energy is going to be when the sun is directly overhead, right? So one way you can combat this, the fact that the sun is moving through the day and the direction of the energy flow depends on where the sun is, right, is you can just make it so your solar panel can move, right? If your solar panel is able to move to kind of follow the sun, then it's going to be way more efficient, right? Would everyone agree with that?
Yeah.
If you can get it so it faces the sun, it's going to be way more efficient. So that's kind of what the Poynting vector is. Is it something that describes the direction that the energy is flowing from, so that you don't think that light is all around us, even though it is, because the light from the sun comes down and it bounces off of everything, and then that's what makes everything lit up, right? But nonetheless, the most energy intensive portion of that light is coming directly from the sun, the original incident light from the sun. All right, so that's the Poynting vector. It has these units of power per unit area. It's basically just intensity. That's usually the way that I think about it. Okay. All right. So I think we can do a problem now. But one other thing to mention is that that commonly what you're going to be seeing in your problems is what's called the average Poynting vector. Okay. And the average Poynting vector is basically just the same thing divided by 2. Okay. So the average Poynting vector is going to be equal to the maximum value of the electric field multiplied by the maximum value of the magnetic field divided by 2 times mu naught, so just 1/2. And I can go through a derivation and show you why this is the case, but I don't think it's particularly relevant. It probably isn't too surprising to you that if I have an electric field that is like a cosine function, and I have a magnetic field that's a cosine function, that when I average them, I get a 1/2 factor, right? We've seen this show up when we did all of our AC circuits. It's just it always happens like that, right? So I don't really feel like deriving this. You can look at a derivation in the book if you want to. It's the same derivation we've done multiple times that involves using the fact that cosine squared is equal to like 1 plus cos 2x or whatever. It's the same derivation. All right. What we can do though is we can do a problem now. This one. Oh, even before we do this, we could say something about solar panels. So, the energy coming from the sun, if you can calculate what this quantity is for the sun. So for the sun, S average is, okay, I'm going to get this number maybe off by a little bit, but I think this is pretty close to what it is. So this is the Poynting vector for the sun. So at the surface of the Earth, this is the value of the average Poynting vector, okay? You could predict that if you went closer to the sun, what do you think this would be if we went closer to the sun? Would it get bigger or smaller? Like if we were on Mercury, do you think the average it's going to be bigger, right? If you're closer to the sun, it's just going to be bigger. That's where the source of the light is. So on the surface of the Earth, this is the average value of the Poynting vector, right? So we can use this to do all kinds of different things. We could use it to figure out what size of solar panel you would need to generate enough electricity for a home. We could use it to figure out what the electric field of the radiation coming from the sun is on average, right? So let's do that real quick, just because I think it's relevant. So let's do a really simple calculation. Let's say you have a home, and we're going to have a really simple home. It's going to be like basically a square, kind of boring home. So here's our house. Here's the door. Here's some windows. And on top of our house, we have just nothing but solar panels. Okay. What are some good dimensions for a house? What if we say that this side over here is like 15 meters, maybe? Maybe this side over here is like 10 meters. Is that reasonable? Regardless, let's say you have 10 by 15 meters of solar panels on your roof. That's a pretty big house, actually. But whatever, we'll go with that. Okay, so the area of this of the solar panels that are on top of this house would be 150 meters squared, right? So suppose you wanted to calculate the rate at which power is produced using this value for the Poynting vector. And let's say that your solar panels have an efficiency rating of about 30%. This is extremely high for solar panels. Or at least it was a few years ago. I'm sure they're getting better. So let's say your solar panels have an efficiency of 30%, and let's say we want to calculate the power that they consume from the sun, okay? And let's assume that this number represents the average over one day, so it includes the fact that at nighttime it's off and at nighttime they're on, okay? So the power would be equal to S average multiplied by the area, okay? So if we take 1,300 watts per meter squared and we multiply by the area of 150 meters squared, the power output of these solar... and we'd have to multiply by the efficiency factor here too. So let's multiply by E, which is our efficiency factor, because we're not going to get 100% of the power. There's always going to be losses, especially with solar panels. If any of you are looking for a good career to go into, finding a way to make better solar panels is a very lucrative field. All right, so 1,300 times 150, and then times the efficiency rating of 0.3, you end up getting 58,500 watts, but that number is kind of not very useful to us, because what's a watt? I think we're a little more familiar with kilowatts. So this would be the power that this would kind of be the power output that you would get from your solar panels. Is about 58.5 kilowatts. So what could you run off of 58.5 kilowatts? Well, you could run a lot of stuff. One light bulb, right? A 100-watt light bulb is 0.1 watts. So if you wanted to run that light bulb all day long, it wouldn't even cut. It would only be a very, very small fraction of the amount of power that you're getting, right? But we don't run our homes just on light bulbs, right? We have things like, let's say you live in an area where, like Arizona, where you need an internal AC unit. An internal AC unit is going to have a power usage of about 5.5 kilowatts. So you could run your air conditioning all day long with this. And again, it would only consume, about 10% of your total power output, right? So now, and this is probably going to be one of the biggest things, the biggest consumers of energy in your home will be something like an air conditioning unit, a heating unit, your washers, your dryers, your microwave ovens, these kind of things. So if you had a home, let's say out in the desert where it's really sunny all the time, like Arizona, and it was really big and wide like this, or you just have a set of solar panels nearby. Now granted, this is pretty big, 10 by 15 meters. It's pretty huge. You could easily use only solar power to basically power your home for a family of 4 with no problem. And that's even though the panels themselves are only 30% efficient. So I say all of this to just point out that there is a huge amount of energy coming from the sun, a massive amount of energy coming from the sun. And we harness at the surface of the Earth a very, very tiny fraction of it, you know? When you look at most homes, they don't have solar panels on them, which makes sense because installing solar panels is extremely expensive. But when you do install them, after a long period of time, they start making you money because you don't have to pay for electricity anymore. Because nowadays, how do you get your electricity at your house right now? You obviously pay for it, but where does it come from?
Sun power plant.
Like natural gases.
Yeah, maybe some of it comes from a solar panel planet. A lot of it comes from burning gases, whether it be natural gas or burning fossil fuels like oil and coal. Some of it comes from renewable sources, such as like hydro dams, like the Hoover Dam and stuff like that. But most of it's coming from burning fossil fuels and stuff like that, right? So hopefully over the next 50 years, you're going to see a lot more solar panels on people's houses because, my God, we've known about this for hundreds of years now, that there was just this free energy coming out of the sun. We've known about the effect of a solar panel and how it works since 1900, basically, with the discovery of what's called the photoelectric effect. And it's really taken 120 years before most of the world is now kind of trying to push for more type of renewable energy. And solar is just one example. You can obviously use wind energy too, and we can use hydro dams too. Anyway, so solar energy, really powerful, ton of energy. Most of it just hits the Earth and never gets used. All right, so the next thing we want to do is to look at the energy of a sinusoidal wave. Oh, I said I would do one other thing. We can also calculate the electric field here if we want to see what the electric field for the sun is. And the way we would do that is to go back here to our definition of S average. So our definition of S average here says that S average is equal to E max, B max, but we know that E max and B max are related to each other because I think B is equal to, E over B is equal to C, right? Which means that B is equal to E over C. So we can put in here E max squared over 2 mu naught C. Can you see how that would, if you combine those two equations together, can you see how this is what you would get?
Mm-hmm.
Okay. And then we can solve for E, right? If we do 2 mu naught C S average, and we take the square root of that, that should give us the value of the maximum electric field. So if we do that, we'll get 2, mu naught is 4 pi times 10 to the minus 7 Tesla meter over amp, and C is 3 times 10 to the 8 meters per second, and then we multiply by S average, which is 1300. We're not going to get a big number here, but so we get that E max, this would be for the sun, at the surface of the Earth. That's important to understand because I think when you're closer to the surface of the sun, this number is obviously going to be bigger because the value of the Poynting vector is going to be bigger. So I got 0.76 volts per meter. Okay. So let's go on to this problem now. So this would be the electric field of the sinusoidal radiation coming from the sun. All right. So here's the problem we want to do. A radio station on the Earth's surface emits a sinusoidal wave with an average total power of 50 kilowatts, assuming that the transmitter radiates equally in all directions. So here's our transmitter down here. In all directions above the ground, find the electric field and the magnetic field amplitudes E max and B max detected by a satellite 100 kilometers from the antenna. All right. So what we're given here is that there is an average total power output coming from the transmitter that's equal to 50 kilowatts. And we want to find the electric and magnetic field amplitudes detected by a satellite 100 kilometers from the satellite. Wait a minute, I'll go back for a second here. Yeah, did I add the 2 in here? I don't know why I feel like I didn't multiply by 2. I did, never mind. Okay, so we have a few equations that are going to help us here. Those equations are S average is equal to E max B max over 2 mu naught. Obviously, the relationship between E and B, E over B is equal to C. And probably also the fact that S average is basically average power divided by area. And why is that? Well, if we go back to right here, the Poynting vector is basically just power per area. So we're given average power, and we're told the transmitter radiates equally in all directions above the ground. So that means that it's going to radiate out into this region here, and it's going to be radiated over the entirety of this hemisphere, basically. So we have a hemisphere whose surface area, the area A, is going to be the surface area of this dome, which I would say would be equal to, I think, 4 pi r squared over 2. Does that seem reasonable?
Yeah.
Because it's only half the dome, and the transmitter's not transmitting downwards, it's only transmitting upwards. Now, if this transmitter was in outer space, it would be transmitting in all directions. And this is kind of a weird transmitter since it's only going up, but I mean, it's conceivable. You could design a device like this, I guess. So our area is 2 pi r squared. And we should now be able to solve for what we want to do. They want us to find the amplitudes of Emax and Bmax detected by a satellite that's 100 kilometers from the antenna. And we should have everything we need here. We are going to have to say that, so if we take power average and we divide by area, that's equal to Emax, Bmax, but we replace Emax using this equation, or Bmax, doesn't matter which one. Let's replace E. E is equal to C times B, so we're going to get C times B max squared over 2 mu naught. And we can solve for that then, so we do 2 mu naught times the average power divided by C times the area. And the area is 2 pi r squared. All of this should be equal to B max squared. So we're going to square root this. So I think the C's cancel. No, the 2's cancel. So it's going to be the square root of mu naught, which is 4 pi, times the average power given, which was 50 kilowatts. That's 50,000 watts. Divided by C, speed of light, pi. R is 100 kilometers, so that's 100,000 meters. This is squared. All of that should give us the value of the maximum quantity of the magnetic field that will be detected by the satellite. What do you all get if you calculate this? That's what I got. Does that look right or no?
Something completely different.
Yeah. I think I left something out. What'd you get?
I got 0.0082.
Like times 10 to the something?
No, like this is like I'm not even sure if mine's right because my scale's completely off.
.0.082, or just that was just your answer? What did other people get?
Yeah.
I got 8.16 times 10 to the negative 11.
Yeah, I think
That's what I got.
that's the right answer. What did I do wrong? Oh, I didn't divide by pi. Divide by pi to the 0.5. Yeah, 8.16. I agree with y'all. So something like 8 times 10 to the negative 11. Yeah, I guess I left this pi out when I did the calculation. So something like we'll call it 8.2 times 10 to the minus 11 meters. No, Teslas. What would suppose that the satellite was like, I don't know, closer. What would the value of the magnetic field's maximum be?
It'd be larger.
Yeah. So like kind of like the farther away that you get, the smaller the magnetic field's going to be because the signal's getting weaker, right? Does that make sense? And part of what the signal is that's coming from the transmitter is really just electromagnetic information, right? And piece of that is the magnetic field. Okay, so then for Emax, we just have to take Bmax and multiply by the speed of light. So Emax is going to be that times 3 times 10 to the 8. So it's going to be 0.024 is what I got. Volts per meter. And that's it. That's the problem. Anyone have any questions?
How do people maybe have like a directed beam? Like what kind of methods would they use? Like,
Oh, that's a really good question. I don't know much about that, but I do know that there are such things as directional transmitters. Yeah, that's what you're talking about. Yeah, I suspect it has something to do with how you're constructing that transmitter, I guess. Yeah, I really don't know, but I know for a fact that there's like, you can transmit your. Let's say you have like a radio station. You want to make sure that your radio station transmit like all around you, right? So you can cover the most possible people to listen to your radio station. But if you wanted to, for example, communicate with a satellite that's far away in space, like Voyager, for example, you'd want to kind of have a directed transmission.
yeah.
And I really don't know much about that kind of stuff, unfortunately. It's not something that I've studied, but it's a really good question. About how
I have seen those like oh my god, is it concave like satellite dishes or something.
Right, so what you're talking about is are you talking about this? The fact that if you have like a concave satellite, and there's like a so the satellite dish right here on like, so this is like on top of someone's house, right? And that if you have a satellite over here in space, like let's say this is like a DirecTV satellite or something like that, and you're getting that this is going to send waves down, right, to your dish. And the way that works is this might send waves off in a few different directions, but the way that your dish actually picks those up is there's like a little bar right here, and there's like a detector right here, and this is placed at the focal point of the satellite. And I think they usually make it so that these satellites are parabolic, or the surface of a paraboloid, where there's this thing called the focus, which is when you have light that comes in from any direction will always bounce to that same point. So if the light were to be coming in, for example, on this side, it's going to bounce to that point. If the light comes in straight like this, it's going to bounce to that point. Is that what you're talking about?
Yes, yeah.
Okay. So I can apply this to something that I do think that I understand a little bit, which is a parabolic mirror works like this in reverse. So inside of your car, you've got like high beams and low beams, right? The low beams just kind of send the light toward the ground, and the high beams send the light kind of straight ahead. I'm pretty sure that works off a similar principle, and so maybe that has something to do with how they do directed transmissions. Because if I reverse this process and I take a parabolic mirror, which parabolic mirror just means it's shaped like a parabola if you rotated it, which I think is called a paraboloid, but I don't really know. And then if you place a light, so you take a light bulb right here, and you place it at the focus, then the light from this beam will bounce off here and go straight. It'll bounce off, even the light bouncing off of here is going to bounce off and go straight. In all the light, basically all rays for the light end up going in the same direction. Is this kind of what you're thinking about?
Yeah, I was thinking about like in reverse. Yeah.
Yeah, it's the exact same idea in reverse. So then this is what the high beams in your car basically do, is they make sure that the light goes straight forward. And almost like very certainly that's probably what they're doing with these directed transmissions. It's just making sure that all of the energy is flowing in one direction, because you don't care, Probably something like that. That seems reasonable, right? Okay. So one last topic. How much time do we have? This is the last thing we're going to talk about, so even if we go a little over, I think it's fine. So we're talking about radiation pressure. And momentum. Oops. Okay. So we have this thing called the Poynting vector, which we said was basically described like this. It's 1 over A, and then you have, I'm just going to put power up here. So it's basically power per unit area, right? And the way that I'm going to do this is different from the way your book derives this, because I feel like this is a little easier to understand. Do you all remember in Physics 1A how we defined power? We defined power as either the rate at which energy is transmitted or consumed, or the rate at which work is done, right? These are basically how we define power. But there was another way that you could define based on the idea that dW is basically the same thing as F dot dV. No, what am I talking about? Not F dot dV, F dot dx, sorry. Because, yeah, that's how work is defined, basically, right? Is that work is equal to the integral of F dot dx, right? So dW would just be F dx. And if you put that in here, what you get is F dot dx over dt, which is just force dot product with dx dt, which is velocity, right? It'd be the x component of velocity. But we could change this to dr, and then it'd be dr dt, and it would just be velocity in general. So this is one way that we can define power. And if we do that in this equation, we can write this as force times velocity divided by area. And for now, let's just assume that the force and the velocity are in the same direction, so we don't need to worry about the vectors. And let's say that since we're talking about light radiation, what am I going to put in here for the velocity?
C.
Yeah, you're going to put the velocity of light right here. So now we have force over area times c is equal to F average. So let's rearrange this a little bit, and we'll write S average divided by c is equal to F over A. Now this is force per unit area. So this seems to imply, when you look at it, that if you have a light beam or any type of radiation, and it has a Poynting vector, which it automatically does, so it has intensity. If you take that quantity and you divide by the speed of light, you get a force that maybe this light can actually deliver force to a location. Now, force per unit area has another name. What is it? What do we usually call force per unit area?
Pressure.
This is pressure, okay? So look at that. You can actually define the pressure of a light wave by just taking S average and dividing by C. That'll tell you the amount of, literally, the force per unit area that it places on the surface. And we could use an example that we just used a second ago, right? The light from the sun, I said, has an average Poynting vector of about 1,300 watts per meter squared. If we divide that by 3 times 10 to the 8, this is actually going to give us an actual value for the pressure of the light beam coming from the sun on the surface of the Earth. What's this? This is going to be a pretty small number, as you would expect it to be. I mean, if you were to go outside right now and you hold your hand out You might be able to feel the warmth of the sun, but you would not think that there's any pressure produced by those light beams. And you'd be right, it's very small compared to air pressure, but it is something we can take advantage of. You get about 4.3 times 10 to the minus 6th. This would be in pascals, but I'm going to write it as newtons per meter squared, because if you haven't seen pascals before, that might be kind of weird. So 4.3 times 10 to the 6 newtons per meter squared. That means if you had an area that was 1,000,000 meters, that the total force of the sun on that location would be about 4.3 newtons, which isn't much, right? That's about 1 pound. So you need to have, what is that? What's the square root of 1,000,000? Is it 1,000? Yeah, it has to be, right? Yeah.
Oh, yeah.
So if you were to take an area on the surface of the Earth that was 1,000 meters by 1,000 meters, now granted that's huge, that's a kilometer by a kilometer, but it's not big by like the scale of the Earth, right? It's just a kilometer by a kilometer. If you were to mark out that area, the total weight of, it's like a weight almost, right? The total weight of the sun on that location would be about 4.3 newtons, 1 pound. 1 pound per kilometer squared. That's what this basically says. But it also tells us that light doesn't just transport energy, it can also transport pressure or force, which means it can also transport momentum. It can make things move. As long as you have a big enough surface, you can actually take advantage of this and actually make things move. Okay, so let's also talk about. So this is the we call this radiation pressure. So your book calls this P-rad. This is radiation pressure. They use I don't like this, but they use the small p for the radiation. I'm not going to do that. We're gonna make it big. It confuses me because we're also talking about momentum, and that just gets really really confusing. So we call this radiation pressure. Right, and as we set up here, it's equal to S average just divided by C. Okay. We can also talk about momentum, because force can also be described as the rate of change of momentum, right? So this could also be written as 1 over A dp dt, where now this P is momentum. Okay, and this is important because we can use these for what are called solar sails to actually make things move. Okay, one thing I have to mention here, by the way, is radiation from the sun can either be reflected or absorbed, right? If you have a very flat pond, the light from the sun comes down and it bounces off of that pond. Some of it goes into the pond, though, because you can see below the surface of the pond usually, right? If you have like a perfectly reflecting mirror and you place it down on the surface of the Earth, the light from the sun is going to bounce down directly off of that mirror, right? So this definition of radiation pressure is kind of incomplete. We say that S average over C is radiation pressure for total absorption, which would happen if you have like a black surface, like tar or asphalt. This is the radiation pressure for total absorption. But when you have a reflective surface, so you have like light that comes in like this and it bounces off like this, it's actually going to contribute double the pressure because the light beam is still traveling. With total absorption, you absorb everything, okay? So when you have this, you're going to say that it's 2 times S average over C is going to be equal to the radiation pressure. So this is going to be for total reflection. That means you're going to get the maximum value of your radiation pressure for a reflective surface, right? Double the amount. Does this 2 make sense to you? So there's
It kind of seems counterintuitive to me.
Does it? Okay. Well, so let's think about something from Physics 1A. So yeah, we're 3 semesters into the pandemic now, so probably none of you have seen this demo. I don't know, but I can describe it in a way that will make sense to you. So say that I take a lump of clay and I drop it from some height above the surface of the Earth, right? And it falls to the surface of the Earth, and maybe it bounces off a little bit, but pretty much that clay is probably just going to splat on the Earth, right? And then let's say that I take a bouncy ball and I take the bouncy ball and I let it go, and it obviously bounces off the Earth, right? The question is, which delivers a larger force? Really, we're going to say which delivers a larger impulse.
Yeah, I'm thinking that momentum must be conserved.
No, it's not conserved.
Oh no. Oh, it's
Well-
not conserved.
Well, because the clay ball, if it hits the Earth, is going to basically go from some momentum to no momentum. And, like, technically, momentum's conserved because the Earth is going to absorb some.
That's what I was thinking. Okay, I was
It's-
kind of thinking in a larger sense.
I mean, the Earth's not going to... Yeah. Momentum is conserved, kind of, in a way. But not really, because this is a situation where the ball is experiencing kind of like an external force from an object that doesn't really move. So, really, the equation for this is that the impulse, J, is equal to the change of momentum, basically. Do you all remember this equation from Physics 1A? It gets used so infrequently. You do, okay. So the question becomes, which delivers a larger impulse? What's going to be the one that has the larger change of momentum, basically, right? Which is obviously going to be the bouncy ball, because the bouncy ball goes from going down to going up, and momentum's a vector. So if it was going down with 1 unit of momentum, it's going up with 1 unit of momentum. It now has a total change of 2 momentum, right? Whereas the clay, if it was going down with 1 unit of momentum, and it drops to 0, it has a total change of only 1 unit. So the bouncy ball has exactly twice as much. That's where the 2 comes from. Does that make sense? And again, if you're not convinced, let me ask you the following question. Go stand outside of a tall building and have one of your friends go up to the top of the tall building and drop things on your head. What would you rather be hit by? A beanbag dropped from 10 meters above your head. That's about 30 feet. That's really high. The beanbag is still going to be moving pretty fast. If a beanbag hits your head from about 30 feet up, it's probably not going to hurt that much, right? Because the beanbag is going to hit your head, and it's just going to kind of be... Most of it's going to be absorbed by the fact that a beanbag is kind of... You know, it's a loose collection of little balls, and it's not going to hurt as much, right? Now, do the exact same experiment, but instead of using a beanbag, use like a hard ball that can bounce. And it's definitely going to hurt when it bounces off your head. Especially if you replace it with something hard like a baseball, right?
Yeah, so I was thinking like, oh, it delivers more of its momentum to me. While like a bouncy ball bouncing off my head, there's still, it still conserves. Not all of its momentum is, I mean, its momentum is changing.
Well, right, but what you have to think about is like, the momentum is changing because there's a force from your head on the ball, which is equal to the force of the ball on your head, right? And you have to deliver a bigger force from your head or whatever, the ground, to push it up compared to just absorb the blow, right? Because you have to take the ball, which was moving down, and you have to push it until it moves up again. The ball that comes down and just goes splat, well, you just have to push it until it stops. So whether you talk about energy, momentum, whatever you want to talk about, in both cases, the ball is having a bigger impact on this point, right? It is kind of counterintuitive, I agree, but definitely the case. All right, so like I said, you can have a perfectly reflecting surface and you get 2 S average over C. You can have a total absorption surface. Like, again, this is going to be something like a black surface. Like something that's really light and white, like white clothing is really good at reflecting light. So that would give you like something like this as well. But you can also have surfaces that partially reflect and partially absorb, right? Like the surface of a pond. When you go look at a pond on a bright day, you can sometimes see your reflection, right? But you can also see through the water, and you can see, into the water, right? So that means that it's partially reflecting and partially... And so when you get something like that, your book doesn't exactly describe this, but I think it shows up in some of your problems. You're going to have a more general expression, which is going to be 1 plus a fraction f multiplied by S average over C. That's going to be equal to the general definition of the radiation pressure, where F is going to be the fraction of the radiation that's reflected. where F equals 1 for a mirror and 0 for other things and something in between for other things, right? Does that make sense? Okay. So F is obviously going to be a number between 0 and 1. I have one more problem we're going to do. Where did it go? Where did it go? There it is. Cut. Cut. There we go. All right. So one of the applications of radiation pressure is something that's called solar sailing. Is it really not going to let me just click? There we go. Yeah, you can't paste it. I get it. All right. Okay. So this problem isn't about solar sailing, but we'll talk about it right afterwards, actually, now that I think about this. Okay, so I guess we just need to zoom in some. Or will this let me... I want to make this bigger. No, there it goes. Okay, it says an Earth orbiting satellite has solar collecting panels with a total area of 4 meters squared. If the sun's radiation is perpendicular to the panels and is completely absorbed, find the average solar power absorbed and the average radiation pressure force. So we want to find the average power absorbed and the average radiation pressure force, which would just mean to find the radiation pressure, right? Okay. Are we going to use the 1300? Is that what we're going to use? Sorry, 1 second. I don't know what we're using for the size of the radiation pressure. Yeah. So your book is using that the S average from the sun. They're using that as equal to 1400 watts per meter squared. Pretty close to the number that I was using. And yeah, we want to calculate these things. So first thing we can do is to say that S average is equal to power average divided by area, which means that if I take S average times the area, I'm going to get the average power. This is like what we did with the solar panel. So this is going to be 1400 watts per meter squared times area, 4 meters squared. So 4 times 14. This is a 1 right here. Can't see it, so I'll just put it. Okay, now I'm going to have to erase it because I made it sloppier. 4 times 14, what is that? 28 times 256. So that would be the average power. And to find the radiation pressure.
And it could just be watts.
Thank you, it is just watts. Thanks. And then to find the radiation pressure, we do S average divided by C. And it says that it is, what does it say? Completely absorbed. It's kind of ridiculous. If there's solar panels, they're going to be reflected, but that's fine. S average is 1400 watts per meter squared. Divide by 3 times 10 to the 8 meters per second. I hope you all think that these homework problems are easy enough. I find that this chapter is really not very challenging with most of them, even if I try to pick the hardest problems. Divided by 3, E8. Because most of it just involves just kind of plug and chug stuff like this. We're going to get 4.67 times 10 to the minus 6th. That's watts. So this is in newtons per meter squared. And actually, it does say radiation pressure force. So I think we want to convert that to force. So the force would be equal to the radiation pressure multiplied by the area. So it would just be 4.67 times this. So if we multiply by 4, then we're going to get 1.9 times 10 to the negative 5 newtons. So this is a really small force, obviously. But one of the ways you can obviously make the force bigger, there's really only one way, right? That's by altering the area, right? So one of the ways that people have ideas of getting propulsion in space without using fuel is by using what are called solar sails, which are basically, you take a vessel that's like you have a really tiny payload, and it's composed of something that has arms that extend out and produce really, really big, sails that are just big reflective. Let me see if I can find a picture for you here. This is not science fiction. This is something we have absolutely done before and proved that it actually works. Here we go. Yeah, solar sails. So the idea is you've got some tiny little object, right, here, and you send out these gigantic sails that are, when you initially launch it, they're not this size, but they just kind of, there's like arms that expand out, and they would be folded up, which is what you can kind of see that there's folds in here and stuff, right? But there's this group called the Planetary Society. Have you guys ever heard of the Planetary Society before?
Nope.
So I think the head of the Planetary Society is Bill Nye, the science guy. You guys have heard of him before, right? Have you heard of him before?
Of course.
Yep.
Okay.
Bill Nye, never.
Okay. I don't know. He's been around for a long time.
That young.
So they sent something called Light Sail 2. So here's an article about this. Solar sailing success. Planetary Society deploys Light Sail 2. The spacecraft is set to harness the power of sunlight alone to alter its orbit on Earth. And they definitely proved that they could alter the orbit of their satellite, like quite literally, just by... apparently it was launched by SpaceX Falcon. The July 2nd. What date? When was this published? Let's see. 2019. Okay. So it's July of 2019. But yeah, like, this is really powerful because one of the biggest problems in spaceflight is that it costs so much money to get things into space, and the cost is based on their mass. So the bigger the object is, the harder it is to get in space. And so if you want to put things into space that can, like, do things for you, they're probably going to have fuel on them, because you need fuel to alter your orbit to get to different places. It's a really powerful idea that you could have something that could move around the vast emptiness of space just by using light from the sun or a star. And it's conceivable that someday we may use something like this to travel to other planets. We would need a really, really, really big sail, but I mean, math is great because, you have this. This is your fuel, basically. The radiation pressure is your fuel coming from the sun, and it's an inexhaustible resource, right? The sun is not going to burn out for like 5 billion plus years. So this is constant. You've got this. All you need to do is to just make the area big, right? As big as you can make this is going to control how much force you can get, which is going to control how much acceleration you can get, which is going to control how fast you can go. And in principle, you could use this to accelerate a spaceship up to the speed of light. Right now, we don't really have that technology yet because we've got it. I mean, this is complicated, right? I mean, you have to produce an object that when you launch it, it's really tiny and compact, and then when you put it into space, it can expand out with all these arms. So it's a problem of material science because you want to have a material that's like really lightweight and reflecting. Because part of the problem is that the more material you have, the bigger the mass becomes, and that's going to affect your acceleration because of F equals ma. So, but nonetheless, solar sail is a really powerful idea. Kind of similar to the way that our ancestors were able to travel and explore the world with the wind of the ocean. Solar sails may be able to travel through the solar system at the very least, off of kind of like the solar wind. The expression solar wind actually means something, so it's not the same thing. Solar wind means all the particles that are coming from the sun. This is just from light itself. But yeah, pretty incredible that light can not only warm our planet, but may be a way to allow us to travel between the stars someday. And that's a pretty powerful idea, I think. Well,
Wow.
Does anyone have any questions or comments about what we're talking about? We believe that light has no mass, by the way, just in case that's unclear. If you're thinking that the thing that could make these things move was coming from photons that were, sending energy in some way that like they have, we think that photons are massless. Photons are like the the particles of light, effectively. And so somehow they can still deliver momentum, though. And you'll learn all about the momentum of light, even of a single photon, in Physics 1D, most likely. And if you do go to take Physics 1D, you're going to start right from here, and you're going to go into discussing light itself. So light is kind of one of the major topics of Physics 1D, right? It's, I think the first 6 to 8 weeks of Physics 1D, you're going to be talking about optics. It's kind of interesting historically. Optics was very well understood long before we understood electricity and magnetism, but then we figured out that electricity and magnetism kind of controlled optics, and so that's why we now teach you E&M first, and then you take optics. Historically, it would have been the other way around. If you were a student in the early 19th century, you probably would have learned optics before you learned about electricity. I would guess. I don't know. But optics is a little simpler. It's interesting. Electricity and magnetism, one of the more complicated topics. You're all done with 1C now. We have the final and stuff, but hopefully you felt like this class wasn't completely awful. I think everybody that comes into this class thinks it's going to be incredibly difficult, and that I don't know. That's just what everybody says. It's just that this course is really difficult. That's what they were saying about Physics 1C when I was a student too, and it's probably never going to change. I think largely because the mathematics that you need to understand this course are pretty complicated, but hopefully we've talked about this stuff in a way that you've gained some understanding of this. Remember, this is only an introductory course, so if you don't understand everything about Maxwell's equations, that's fine. That's not the expectation of a course like this. This is an introductory course. We're just kind of introducing you to these concepts so that when you study them later, like if you go on to become an electrical engineer, hopefully some of these ideas will resonate with you, some of these ideas will stick with you, and will help you to get through your later electrical engineering courses where you'll go into a lot more detail. And if you're going to study physics, you're going to be studying, or even if you just take some advanced physics classes, if you're a math major or something like that and you're interested, you can go and take advanced versions of electricity and magnetism. You can learn more about this stuff. I will say that those advanced E&M courses are kind of interesting, but really the reality is that you're going to cover almost all the same concepts that we covered. It's not like they're going to teach you anything brand new. They're just going to teach you kind of like ways to use other stuff from your calculus course that we didn't talk about. Like we never talked about Green's functions in this class, right? But they're very useful for analyzing certain electromagnetic systems. So anyway, we're probably going to, at the very least, take a break here, but I just kind of want to get some feedback from you guys. Do you guys want me to do some kind of general review of all of E&M after we get back, or do you all want to just stop right here? What do you all want to do?
Review, please.
Okay, it's going to be really short. It's probably going to be maybe 15 minutes most. So we're going to take a 10-minute break, and then we'll do a really, really short review.